In this lesson, we will update and finalize our hypothesis based on our findings from research and testing. We will also work with information security teams to define requirements for testing and developing analytics within their environment. Finally, we will utilize the analytic development process to scale testing of our analytics. Now that we've completed our tests, we can go to the right side of the threat hunting methodology V diagram, where we can develop and implement our detection analytic. As we found in our testing, the metadata on this slide are the invariant behaviors which identify the behavior of token impersonation and theft. In Windows Event IDs, we identified a 4624 event, also known as a successful logon event, with a logon type 9, no elevated token, impersonation level of impersonation, logon process ADV API, and negotiate authentication package. Mandatory label of medium was detected across all tests, but was not in the 4624 event. We also identified a registry key, which is set through Sysmon event ID 13 in the background activity monitor to the specific application. With these invariant behaviors, we can take them and translate them into a new hypothesis to detect behavior within our environment. Due to the nature of our environment, we will be focusing on Windows Event IDs. In Lesson 2, we created our initial hypothesis. If duplicate token X, impersonate logged on user, SetThreadToken, or impersonate named pipe client is detected with other malicious behavior, an adversary is attempting to conduct access token manipulation by performing token impersonation or theft. Now that we've identified behaviors, we can translate and fine-tune this initial hypothesis into something that can be translated into our SIM instance. We can take the items in red, which are the less specific terms we found in our research, and fill it in with the metadata we found in our testing. So, if we take the metadata from the invariant behaviors from the logon event, we get the following updated hypothesis. If a successful logon event is detected with a logon type 9, no elevated token, impersonation level of impersonation, logon process ADV API, and negotiate authentication package, or if a registry key value is set with background monitor, or if a named pipe is impersonated, an adversary is attempting to conduct access token manipulation by performing token impersonation or theft. To get started testing within your information security environment, we now need to translate our hypothesis into an analytic. We can take the purple highlighted words and input our findings from our testing. We will be focusing on our Windows Event ID behaviors, which can be translated into the following. Source type equals event log, event code equals 4624, elevated token equals no, impersonation level equals impersonation, authentication package equals negotiate, logon type equals 9, logon process equals ADV API. Now that we have our analytic, we can begin to operationalize our analytic within our environment. Another analytic idea we can pursue is identifying the impersonate named pipe client attack. As Ryan discussed in the previous lesson, Sysmon Event 17 and 18 will identify when an adversary has created a pipe and the pipe has made a connection. For this lesson, we will not be focusing on building out the remainder of this analytic. However, it is definitely something which can be pursued if you collect Sysmon data or other data that can identify the creation and connection of these pipes. An idea which can be pursued for this analytic is to create something sequential to add more context to the token impersonation and theft attack. For example, when event 4624 is detected, is there a linking of Sysmon event 17 or 18 occurring afterward? How can you link those events together? This is just one of the ways we can use a robust analytic, like the one we are developing, to develop lower tier or less used analytics to provide more context for the adversary behavior. Operationalizing our analytic is the next step in our process for detecting adversarial behaviors within our environment. However, it's not as easy as just putting your analytic into a SIM and expecting to catch the bad guys. We need to validate our analytic effectively, detects adversary behavior, ignores benign behavior, and can be translated into the SIM environment. This is where we can start working with information security teams. They will be the ones who will eventually implement the analytics and determine if they meet the requirements set by their team and the greater organization. Before going about testing, it is important to understand their process behind implementing analytics and work with them to ensure they are truly effective. A couple of things to keep in mind while working with your team include the following. Is there a specified testing environment which must be used before analytics are pushed to production? In most cases, teams don't push to production right away, as sometimes things can break systems. Understand what their processes are for testing, including timelines and testing environments. Second, are there a certain number of false positives an analytic cannot exceed given a specified time frame? Analysts don't have time to go through all alerts which come through, and decreasing the number of alerts which do come through is crucial for analyst efficiency. For example, based on research, junior analysts are assigned 1 to 2 sensors and can handle, on average, 5 alerts per hour. If an analytic does not effectively filter benign behavior, analysts can sink under the number of alerts they need to check. Is there an allow list for specific programs and applications? Some programs might indicate malicious behavior, but are cleared and verified by security teams to be benign. Finally, are there existing analytics related to the current testing hypothesis that can be updated? There is no need to reinvent the wheel. If there is an analytic your information security team has already implemented for your identified technique, see how you can help them improve it using your research and testing. Being able to expand scoping while building an analytic is crucial, as running tests on your local machine is significantly different than monitoring hundreds or thousands of different machines. Our terrain will change over time as we work with our information technology group and shift gears. We start with testing the analytic in our local testing environment, ensuring our analytic detects the tests we ran and filters out false positives. The time period of where we look for detection is pretty small, probably just looking over when we ran our tests. We then move into our detection environment. This environment can include other systems and processes, and we need to test that our analytics still pulls back the tests we ran and filters out benign behaviors. We can also define false positives and add exceptions to programs we deem sufficient to pass through an allow list. However, this list should be kept small, and we will get into that later in this course. Our time frame increases as we can begin to test over a time period of a couple hours or a day. Finally, after our analytic has been deemed effective, we can submit our analytic to the information security team to be pushed into a production environment. This segment might have a testing window as well to ensure the analytic will work and run the way it's defined to run. However, this will be the step where we begin to operationalize the analytic. Our testing time window will cover multiple days to weeks to ensure it is covering the alerts analysts will be seeing. After it has passed this test, we can push to production. Our team at MITRE went through this analytic improvement process to implement our analytic into our environment. We will now break down each step in the process and describe our steps as we accomplished it. First, we focused on identifying our emulated test behavior within our local environment. This was the machine we ran our tests on. Through filtering processes, we were able to write an analytic which did not generate false positives. Due to logging limitations on my local machine, this was tested over a time span of a few minutes. Next, we moved to testing to the developer and testing environment. The scope of this testing was enlarged a bit as the environment contained a few hundred machines and had greater logging capabilities. The major difference between my machine and the testing environment was the number of false positives that were generated. There are hundreds of users on this system which are using different applications and processes than me. I needed to create a more robust analytic that encapsulated behavior from a large group of users. Through some extra development and testing, we were able to create an analytic which only generated a few false positives, under the limit deemed acceptable by our information security team. The programs were deemed benign and were added to an allow list. The testing window was also expanded, as our final analytic was tested from a time span of 4 hours to 7 days. Finally, we can move to the final step of implementing our analytic into our production environment. Before our analytic was pushed to the production environment, it was pushed to a separate SIM to ensure nothing would break or generate too many false positives. The analytic picked up a few findings, but they were considered benign by security analysts. The logs were also tested over a 30-day period. After a sufficient testing period, our analytic was operationalized. In addition to our analytic being operationalized, we also must consider our blind spots. While our analytic has been tested and can cover multiple implementations, there are items we can miss. Documenting these blind spots is crucial for further development and communicating these results to your information security teams. First, what are the current blind spots? Were there multiple programs or processes added to an allow list that are not covered from this analytic? we also need to come up with ways to mitigate those risks from the exclusion. Whether the programs are being monitored by other programs or are removed from the system, this list should continue to grow as time goes on. Second, how difficult is it to evade the analytic? This would be a great time to work with your red team or penetration testing team to collaborate about building better analytics. Have them review your research and final analytic. Is there anything they can do to evade the analytic? How can you take that information to make your analytic better? How many implementations does the analytic detect? While our research was focused around creating a robust analytic to detect multiple implementations, it is difficult to gather information on everything out there. Again, it is important to document this moving forward and finding ways to continuously improve analytics in the future. Finally, how fast does the analytic detect malicious behavior? This will depend on a multitude of variables, including where the data is coming from, also known as the sensor, how long the extract, transform, load process takes, also known as the ETL, and how the analytic itself is designed and implemented into the SIM environment. If an analytic takes a minute or more to go through logs, it might not be super helpful in detecting behavior. How often are the analytics run in the SIM instance? Recognize timing and attempt to make the analytic more efficient, especially as the analytic covers more implementations. Our analytic is without exception. Here are some of the detection gaps our team identified when creating our analytic. When we were building our API calls, we used certain flags which worked in the environment we were testing in. This included the logon32 logon new credentials logon type and the logon32 provider WinNT50 logon provider, which utilizes the negotiate logon provider. However, this might not work in every environment. More importantly, this might not cover all logon options for your environment. Ensure you test all options you can, update your analytic, or provide other tools or logging to mitigate for this gap. After completing my research, I sent this over to our adversary emulation SMEs and asked if they could avoid this analytic or how I can improve this analytic. One option they said could occur is avoiding the logon process entirely. Is there a way in which you can bypass the logon process entirely and just focus on abusing the token itself? We are continuing our research to account for this gap, but for now, this seems to be our best return on investment. In addition, we noticed in our testing the existence of an elevated token. This identifies the process is occurring at an admin level. This process can also occur at a non-privileged level. We could build analytics to detect both. However, for the purposes of this attack, the adversary will most likely be looking to escalate privileges and move laterally within an organization. In addition to finding gaps within our testing and evasion, we also need to consider the applications which might be allow listed while utilizing this analytic. While we want our analytic to have high precision and high recall, it is difficult to achieve both. Specifically, our analytic might alert on false positive, which we deem are safe but too noisy. Allow listing these processes or applications might be beneficial in filtering out noise, but we need to ensure we have other mechanisms for detecting malicious activity associated with these processes, more specifically, on applications which use the new credentials logon type. After testing through multiple implementations, our final analytic is as follows. Source type equals event log, event code equals 4624, elevated token equals no, impersonation level equals impersonation, authentication package equals negotiate, logon type equals 9, logon process equals ADV API. We went through an iterative process which we determined how to best shape the research into an analytic. After a few weeks of testing, we were able to create an analytic to detect our malicious behavior. A few false positives were caught while testing our analytic and filtered out of the system. Now, we can continue on to sharing our results. Now, analytic development is not a one-and-done task. It is something that takes care and feeding throughout its life, hence the analytic development lifecycle. First, analytics should be revisited at least once a year, if not revisited on a more continuous schedule. Things can change quickly in an analytic environment. New threats or attacks can emerge, company environments can change, or programs can change processes which can set off an analytic. In addition, is the analytic still producing anticipated results? Are there more alerts than usual? Is the analytic not producing any alerts? Revisiting the analytic ensures our hard work is put to good use and promotes the mindset of a proactive approach to detecting adversary behavior by keeping up to date with new and emerging threats and technologies. One way to keep more up to date with analytic metrics is developing appropriate visualizations and dashboards. This will allow responsible parties to easily track changes, detect changes in behavior, and determine if something needs fixing. Finally, having investigation and incident response playbooks attached to your analytics. This will be crucial to effectively respond to assumed and confirmed attacks or breaches in an organized fashion. The responsibilities of analytic lifecycle management after an analytic has been implemented should be discussed by the appropriate teams. This is definitely not a one-size-fits-all approach. Although no one team may handle responsibility, this effort should be collaborative across various skill sets, and teams should ensure analytics are effective at detecting adversary behavior. Let's revisit our organizer and add in additional information we found throughout our analytic building process. First, through our testing, we were able to clarify one of our benign cases which we can track for future development. These are logons used by internal processes and applications. We can work with security teams and perform SIM research to identify these applications to prevent collecting false positives in our research. We can add in our updated hypothesis, which can include the language which we use to translate our potential analytic to a more technical wording for translation into pseudocode. Finally, we can add in our low variance behavior analytic for token impersonation and theft. Congrats! You developed an analytic for token impersonation and theft. In this lesson, we finalized and translated our hypothesis to a language usable for testing. We defined requirements for testing by working with an information security team. We utilized the analytic improvement process to scale testing of our analytic. Finally, we created a final analytic while identifying blind spots created through testing.